Hello there, ladies and gentlemen. So you should have your notebooks open to page 53. We're going to write down the schedule here real quickly, what's coming up for the next week or so. Today we're going to be doing the notes on modern atomic theory. If you're a B day, these are actually backwards. B day is doing it on the 11th, and A days are doing it on the 12th. And then B days, next class is 15th, A days is 16th, because we're going to be backwards for a little while here. And then the 17th and the 18th and the 19th and the 22nd. So my B day students, you all are taking your test on the 19th, and A day you are taking it on the 22nd. So we're going to be talking about modern atomic theory. This is the idea about how electrons move around the nucleus and what patterns they move, and then how that impacts bonding and a bunch of trends that are on the periodic table. We're going to cover a lot of stuff. Since you're watching the video version, you're not going to get all of the fun background stories. You're not going to get to see the demonstrations, but I will be doing the demonstrations in class next time. Before we get too far into the notes, I want to point this out right here. Let's actually kind of underline it or something like that. Here you go. Polyatomic ion quiz 1, the names, that's on the 17th and 18th. More on what that means, but write that down, highlight that, put that on your calendar. We'll talk about that in just a second. All right. Lots of vocabulary. As you look at the vocabulary at the bottom of that page, there's a whole lot of things you're not going to recognize. This chapter is going to be filled with vocabulary. Make sure you spend some time getting to know the vocabulary. We tend to ask homework questions that are more focused on practicing the ideas, not on the vocabulary. It's your responsibility to go back and make sure you know what the different vocab words mean. Otherwise, when you get to questions later in the year, you're not going to have any idea what the question's talking about. And then on the back of that page is all the things that the county and the state say you need to know, which we are not going to read, but that's on the back of your page. Okay. I mentioned the polyatomic ion quiz. If you go to the very first couple pages, you know, back where the elements were, this is like page VII or something like that in your purple packet. There is a list of 13 polyatomic ions. Our first quiz is going to be the names. So I will give you the formulas, and you need to give me the names. So you might see CrO4 minus 2, and you have to tell me the name of CrO4 minus 2. Yes, you have to spell it correctly. You know, I mean, the tiniest amount of wiggle room, but a misspelling could be a huge deal. If you misspell, you know, this word from nitrate to nitrite, nitrite and nitrate have completely different properties. So what the heck is a polyatomic ion? A polyatomic ion is a group of atoms that are bonded together and they have a charge, and they're common groups of elements that we see all throughout nature. Your genetic code is made of sulfates and phosphates. You're eating nitrates. There's nitrates in fertilizers and ammonias, ammonium, and lots of things that you guys see on a regular basis. So we have a list of the 13 common ones. These are the common ones. There's actually 118 polyatomic ions. These are the 13 common ones. You need to know the names by that quiz next week. Make flashcards. In fact, I'm going to give you some time today to make flashcards. All right, so modern atomic theory. We kind of have the evolution of our view of the atom. First we have John Dalton. Yes, draw this picture and write it down in your notebook on page 55. First we have Dalton's billiard ball or sphere model. Then we have, oh, that's not Lord Kelvin. That is not Lord Kelvin. Who actually came up with the plum pudding model? J.J. Thomson. There we go. So let's just pretend that it doesn't say Lord Kelvin. Dang it. Thought we had gotten them all. Alright. So J.J. Thomson developed the plum pudding model. That was where you had the positive charge with the electrons jammed in it. And then Rutherford with his gold foil experiment brought us the nuclear model. That was focused just on the nucleus and not so much on the electrons. Then we move forward to the Bohr model. This is a very boring model. This is where you have electrons on orbits moving around the nucleus. And then today we're going to talk about the quantum mechanical model. The quantum mechanical model can't be attributed to just one person. It's really more of a team. Heisenberg and de Broglie are two of the main people responsible for the math, but it is a very, very heavy math-based problem. We do not do the math. We're just going to look at the pretty pictures. So this is a lot of the background, which we're not going to get into in this video. These are like the more interesting things. We're going to cover some of this background stuff later on. But as I was saying, there was this dream team of scientists, and maybe you don't recognize this as the basketball dream team from one of the Olympics. But this is the dream team of scientists, where these people all got together in 1927, and you have everything from Einstein to Curie in here, and a whole lot of other really famous scientists you maybe haven't heard of, like de Broglie and Schrödinger. Heisenberg's very, very popular, and Bohr, Max Planck, Henry Lorentz, all these guys. And you see, this is the Conference on Electron and Photons. And yeah, you'll notice this is a very European group. And the reason this is a very European group is it's 1927 and travel is not an easy to do thing. So it's mostly Europeans here. But only one of these scientists won 2 Nobel Prizes, and that would be this lady, Marie Curie. Yeah, okay. So, electromagnetic radiation. Electromagnetic radiation is these waves of light that are moving through the universe. The fundamental unit of light is the photon. Let's see if I can write that on there. A photon. So photons are flying through the air right now, and you can see them. If they're in the visible spectrum, there's a whole lot of light waves we can't see. You can't see gamma, you can't see X-rays, you can't see UV. You can see the Roy G. Biv. It's a very small portion of the light in the room is actually visible to you. And there are 3 parts to a wave. There is its wavelength. There is the amplitude, and there is the period of the wave. Those are all too big, but you can fit that in there. The wavelength is literally how long it is. I might also say the speed or velocity, but we don't typically worry about the velocity because the velocity is constant, and we're going to talk about that in a second also. So wavelength and frequency and speed. Wavelength is literally how far one wave is from the next wave. It's the distance. Frequency is how often a wave passes, and then speed is how fast it's moving. Now, all forms of photons move at the same speed. We call this speed the speed of light, and here is the value, 3 times 10 to the 8th meters per second. Yes, you need to know that the speed of light is 3 times 10 to the 8th meters per second. Maybe circle that or highlight it. And the abbreviation or the symbol that represents the speed of light is c. The symbol for wavelength is lambda, this thing that looks like a Y has been flipped upside down. And then how often it occurs, the frequency, is this Greek letter that looks a lot like a V. It's called nu. So which of these has the greatest wavelength, which has the greatest frequency? So they're all moving at the same speed. So this one, the same. All of them should be moving at the same speed because they're light waves. They should be moving at the speed of light. Which one has the greatest wavelength? It looks like the red one. Red has the greatest wavelength. It's the greatest distance between waves. And then the blue one appears to be occurring the most often, so it has the greatest frequency. And this is true. Red wavelengths are longer, they're a less frequency. When you see blue, you're seeing more waves per second because they're higher frequency. We have this beautiful Roy G. Biv spectrum. I know Might not look like that in your book, depends on whether or not it printed out in color or not. So there is the Roy G. Biv, and then there's gamma all the way down to radio waves. You should know that gamma rays are the most intense, the highest frequency, and that radio waves are the least intense, the lowest frequency. That's why we use radio waves for a lot of our communications. They move at the speed of light, so it's practically instantaneous, but they don't have much intensity, so they're a lot safer. You could have a gamma ray cell phone that would be the best signal ever. It would also irradiate your body, so that's not good. How does wavelength and frequency relate to the energy? So just, all right, went ahead and filled the words in so that it was easier. So there's different wavelengths of light, you know, the red, orange, yellow, green, blue, indigo, violet, and each wavelength carries a different amount of energy. The photons of red light carry less energy than photons with blue light. It's really a matter of how many waves we're getting per second also. The longer the wave is, the less amount of energy is carrying. The shorter the wavelength is, the higher amount. And it's also a matter of the fact that if they're shorter wavelengths, you're getting more waves per second, more photons per second. Here's one of the weirder things is that light behaves as both a wave and a particle. So you've probably seen your sine waves or cosine and stuff like that in a math class. You know, where it goes up, down, up, down, up. And this is how light behaves. It actually travels as a wave, but it also travels a straight line like a particle at the same time. So this is really confusing, but light can be both a wave moving like a wave moves and like a particle traveling a straight path, and we've done tests at the same time. I'm always curious as to what people see down here. A lot of people see light is a particle, P-A-R-T-I-C-L-E, and then other people see light as a wave. And it's a fancy little way of saying it's both. And then this exclamation point is showing a wave, but it's also showing a dot, like a particle. So it's kind of representing both ideas, that light can be both. So what is a photon? A photon is the light particle. It's the particle of light released as electrons transition between different energy levels, which we're going to get into in a minute. And it takes a certain amount of energy, or quanta, and we can split light apart into different wavelengths and into different photons, and we're actually going to do this in class next time. We're going to excite a gas and then split it apart, and we can see all of the different wavelengths contained inside the light. When an excited hydrogen atom, when an atom of hydrogen is excited, it can release a certain amount of energy at certain wavelengths. And it always exhibits the exact same wavelength. So anytime you heat up hydrogen or excite hydrogen, you get these these four wavelengths of light that we can see. And it never varies for hydrogen. It's always those four. And so we start to try to figure out, well, what's going on? We excite hydrogen. Why are we only getting these four wavelengths? And by excite, we mean we're running energy through it, running electricity through it, and we're bumping electrons up to different energy levels. And that we found out that hydrogen has set energy levels. So an electron can only jump from, say, step 1 to step 4. It can't hit any of the steps in between. And when it drops back down, it can only drop back down to step 1. And so we start to kind of look at this, and this is where the Bohr model first comes from, is that there's different energy levels or distances from the nucleus, and electrons can only exist at those specific values. These two terms, excited and ground state, so you have an electron here on the first energy level. Here we go. Okay? And it gets hit with some energy and it gets bumped up. Well, as it gets bumped up, it could go to 2, It could go to 3. I guess I accidentally started it on energy level 2, didn't I? Let's put it on 1, sorry. So it's here on energy level 1. It gets excited as the electricity is pushed through it or gets hit for some reason, and it gets bumped up to 4. There we go. So now it's at 4. Well, it can only move back down to an empty space. Well, there was a couple empty spaces here. At 4, it could move to 3, 2, or 1, and we can get different transitions. And as it moves from one level to the other level, it releases light, and we can see that. But can only release light if it's moving from one energy level to another energy level. And there is no energy level 2.4. There is no energy level 3.1. It's got to be that exact value. And so as electrons move from the closest location to an empty outer location, we are saying they're moving from a ground state, the closer energy level, to an excited state, one that's farther away. And they're constantly transitioning back and forth between the ground state and the excited state. And as they drop back to the ground state, we get to see the light that is produced. So Niels Bohr is the one that kind of figured this out, and he put together the Bohr model. It's the idea that there's a nucleus and that electrons could jump between energy levels, and gave us a new model. And this model was very successful. It really explained, say, the first 20 electrons really well. The first 20 electrons, first 20 elements, everything up through calcium was really explained well. It was once we hit some of the other elements past calcium that the Bohr model started to kind of fail us. And that brings us to new models. You know, when the model you're using doesn't work, you have to do some more research. That's just part of science. When it's not quite completely understood, you study some more. And we have one more slide here actually on two terms that I thought I'd skipped. Emission and absorption spectrum. Just like the energy can only be given off at certain energy levels, it can also only be absorbed at certain energy levels. So if you shoot light at helium, or you shoot light at argon, it's only got certain energy levels it can move through. So we see the two at the same time here. We see one where it's absorbing and one where it's producing. So, you know, just as you can excite hydrogen's electrons to certain energy levels, they also only absorb at certain energy levels. So if you shoot light at hydrogen, most of the light just passes right through. At certain wavelengths, though, it does get absorbed. And at certain wavelengths it gets emitted, and so these two emission and absorption spectrums mirror each other. But if you shoot yellow light at hydrogen, you get nothing. It doesn't get excited, as just like it's not being absorbed. But at this one wavelength here, if you shoot that wavelength of light at hydrogen, it will get absorbed, and then it will be released also. That's pretty cool. Here we could see like every element kind of has its own pattern, and we can actually look at elements as we excite them, and we could see this pattern. And one of the most exciting things about this was when we discovered helium. We discovered helium by seeing this pattern, seeing helium's pattern, that is, in the sun. And no one had seen helium on the planet yet before that. So it was actually discovered in the sun first, seeing a new pattern for an element that hadn't been discovered. One of the fun things we do is we will burn different elements, and we'll look at their various colors. This is a fun lab we usually do, and each element has kind of a unique color. It can be kind of hard to tell the difference between like sodium, which is that color, yellow-orange, and calcium, which is a darker orange. That can be really hard for some students, but it is really interesting. It's a fun lab. We burn stuff. No one who loves burning stuff. Everyone does. Back to the words. So the wave mechanical model is the current model we use, or it's also called the quantum mechanical model. It is very math-based, and it describes electrons moving around as waves, but they're not in orbits. They are located in something called orbitals, and these are locations where we expect to see these electrons as they move around in these orbitals. And we're going to look at some pictures of orbitals in a second. But orbitals can be found in different energy levels, just like we had energy levels in the Bohr model. But then we take those energy levels and we break them apart further. We break them apart into sublevels. So there's 4 types of sublevels: S, P, D, and F. And those S, P, D, and F are descriptions of a big, nasty math problem. We're actually going to look at the math problem for about a second. I might start crying, and then we're going to move on because we don't do the math. So we're going to take electrons, we're going to place them on energy levels, and then we're going to say, okay, inside that energy level there's also these sublevels, like an S and a P, or maybe a P and an F sublevel with different regions with different shapes. And then inside that sublevel are some orbitals. And then one kind of key thing down here, why did I pick that? One kind of key thing down here is that orbitals can only hold 2 electrons. Let's emphasize that. Orbitals can only hold 2 electrons. Right? So you might need to write that down in your notes or underline it or something like that. So let's look at some crazy pictures. Oh, yeah, this is the math. So you've never seen any math like this in high school. And if you're lucky, you might not ever. Believe it or not, we had to take some math classes at some point that the chemistry teachers that had some of these weird looking symbols, that's psi, and that's lowercase delta, and we had to do some nasty math. This is the math behind the pictures we're looking at. Again, we don't do this in high school. So what do orbitals look like? So each of these are orbitals, and they can hold how many electrons? 2. Very good. So they can hold 2 electrons. The S looks like a ball or a sphere. The P looks like these 2 balls on each side. And the D is actually got 4 spaces, and then the F. But I want to make it clear that each of these can actually only hold 2 electrons. So you could put 2 electrons in here. Put 2 electrons in here. Put 2 electrons in here. Put 2 electrons in this shape, and then you keep that going. Each of these can only hold 2 electrons. We'll keep going all the way across. Oops. Let's get out of that one. So you can keep going and just keep adding 2. I'm evidently struggling all of a sudden. Good thing I'm not recording this. And the electrons slowly build up in spaces around the nucleus, and again those spaces are called energy levels, and then sublevels, and then orbitals. And orbitals have different shapes, and depending on which sublevel you're in, they're in different shapes. Now, I put all these crazy shapes up here. No one can draw these by hand. You're not going to be asked to draw these by hand. You might be asked to describe the S and the P, but you're not going to be able to describe the F. This looks like freakish is what it looks like to me. But these are the different shapes for where electrons are moving. And keep in mind, in the center of each one of these, so in the center would be what? What's in the center of every atom? The nucleus, right? So moving around inside this ball would be 2 electrons, and at the center of that would be the nucleus, the very tiny center. Alrighty. And these orbitals kind of build up around the nucleus. So we have a nucleus in the middle. I have a sphere kind of in purple here, and then another sphere, another s orbital, and then those weird P shapes. So the P's were these 1, 2, 1, 2, 1, 2. And look, here we have them. 1, 2, top down, 1, 2, front, back, 1, 2. So they slowly build up around the nucleus, and these orbitals each can hold 2 electrons. And wait, if you can see real lightly, there's another sphere out there. And so this atom looks like it has s orbital that's really close, and then it has another s orbital, and then it's got a bunch of p orbitals, doesn't it? And then it's got another s orbital. Starting from the middle and working my way out, on the closest energy level, there's an s. On the next energy level, there's an s. And then there's a p, and a p. That's 3 on the second energy level. And then another sphere, a bigger sphere. And each of these could hold 2 electrons. So we're just going to try to type that also. 2, 2, 2, 2, 2, 2. And how many electrons would that be? It would be 20. That would be 20 electrons. So we can describe where the electrons are around the nucleus by saying what energy level they're on, what shape or sublevel they're moving around in, and then how many electrons are there. And this is one of the main things we're going to do, and I'm going to explain that again and what the tools are for doing it. So again, s orbitals look like a sphere. P orbitals look like, they're usually called dumbbell shape. I usually say they look like a peanut, actually, because they're kind of thin in the middle and heavy on the sides, like a lot of peanuts are in the shell, not the other ones. You keep them in the shell. People are allergic to them, so you leave them in the shell. And then the d orbitals are those wacky shapes. There's 5 of them, and the f sublevels are also 7 wacky shapes. And sometimes there's only 1 electron. Maybe you run out of electrons, so it's half filled. Sometimes it's all the way filled. So we're going to spend most of our time doing electron configurations. And electron configurations are writing out the order in which the electrons are filling up. You're saying, there's 2 electrons, and then there's and describing exactly where these electrons are around the nucleus. And we'll go through how to do this. We're going to use Aufbau's order. Aufbau's order is actually on the back of your periodic table. So let's pause the video and you guys get out your periodic tables. And actually, it's probably a great idea that you're getting your periodic table out, because I can see you in the corner over there have started to doze off. Can you wake him up for me? Thank you. Thank you. Good, good, good. Okay, now that we're all back, we got our periodic table. We're flipping over and we're looking at Aufbau's order. Those of you who know German, you might know that Aufbau stands for to put in order. So this literally means to put in order, which is just silly. But on the back of your periodic table, you have this thing called Aufbau's order, and this is the order in which electrons fill around the nucleus. And it's actually very easy to use. The only problem is that you've spent your entire life being trained to go left to right and then top to bottom, and this is not that at all. This is the weirdest pattern, but it's right there on your back of your periodic table. First of all, focus in on the idea that there are arrows on this order. Look at that. There are arrows there. If I go pause. And I have labeled this start here. And then you follow the next arrow, and you follow the next arrow, and you follow the next arrow. And you are slowly building up electrons around the nucleus, and you're describing where all of the electrons were. We're going to quickly do iron. So look at the front of your periodic table. You find iron, and it has 26 electrons. So these 26 electrons are all located around the nucleus on different energy levels, in sublevels, and then in orbitals around them. And we're going to use Aufbau's order to describe where they are. So the first energy level only has a 1s, right? This is the first energy level, sublevel, number of electrons. First energy level, sublevels, the s, which we discussed was the sphere shaped, and then there's only 2 electrons in there. All right, since there's 26 electrons, we've got a ways to go. So we go down to the next arrow, and it says there's a 2s, and that can hold 2 more electrons. So that's only 4 electrons so far, so we've still got quite a ways to go. After this arrow, we go to the next arrow, which is the 2p. All right, superscript 2p. holds 6 electrons. Great. At least we got a bunch done that time. So we have 2, 2, and 6, which adds up to 10. We're making some progress. After the 2p, follow the diagonal down and you hit the 3s. Okay. The 3s, how many electrons can that one hold? I look right here, the 3s can hold 2 electrons. Alright. I can put a 2 there. And that is now 2, 2, 6, 2, that's 12. So we're getting pretty far. What comes after the 3s? Alright, you go to the next arrow, and this is where people start to mess up, which is why I'm kind of doing it so slowly. After you finish with 3s, you go to the next arrow, you slide down, you have a 3p, and then the 4s. You have to follow the diagonal all the way. You can't go halfway down the slide and then jump to another slide. You have to literally finish the slide you're on. So please, finish the slide. Oh, what just happened there? I don't need a 6 over there. There we go. So we're 3p6, and as we finish that slide, it goes to the 4s. Having some technical difficulties here. Alright, so let's pause and do a count here. 2 electrons on the first energy level, 2 more electrons on the next energy level, 6 electrons still on the second energy level. That was 10 electrons total. Now we have 12 plus 6 is 18 plus 2 more is 20, and if you recall, there's only 6 more electrons. So I finish this slide. Where do I have to go? After I finish this slide, I got to go to the next slide. The next slide says 3d10. So let's write that down. That's going to be a mistake, but we'll write it down anyway. 3d10. If I do 3d10, let's do the math. 2, 2, 6, 2, 6, 2, 10 adds up to 30. Do we have 30 electrons in iron? No, we have 26. So, what if I had just written 3d6? 3d6 adds up to 26, and what we're saying is that not all of the spaces are being used in iron, which is what gives iron some of its properties, is that not all of the space that's available, and by space available, I'm going to flip back here a couple pages. Remember this? We said out of the D's, there's 2, 2, 6, 2. All of these can hold 2 electrons. Oh, we could go 1, 1, 2, 3, 4, 5, 6, and there's still space for more electrons. And this is what gives iron some of its unique properties, and this is what gives every element its properties, is how those electrons build up, where there's filled locations and where there's half-filled locations. And so what we've done here is we've written out where iron's electrons are. And when we do this writing out of where they are, this is called an electron configuration. Alright? This is called an electron configuration. So let's try chromium. Chromium has 24 electrons. So how would chromium be different from iron? Look, it's so similar. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, but it has 24 instead of 26, so it's only got 4 at the end to get up to 24. I want you guys to take a second, pause the video, and try sulfur and zirconium. Step 1, of course, is finding the elements on the periodic table and how many electrons they have. And then step 2 is going to be working through their configurations. Alright, use off-Bose order, work through the configurations. Okay, so it took me about 3 minutes to do these two. I'm typing, you guys are writing by hand. So I was using off-Bose order. I saw that sulfur had 16 electrons, and I slowly wrote down the order following the pattern on the back of my periodic table. So sulfur has 16. 2, 2, 10, 2, 4. That's 16 electrons. Zirconium had 40, so this took a lot longer, and I had to go I had to go 1s2, 2s2, 2p6, 3s2. Next slide. 3p6, 4s2. Next slide. 3d10, 4p6, 5s2. Still wasn't all the way through all the electrons I had. Next slide. 4d2, 4, letter D, number 2, and then I had gotten through all of the electrons that zirconium had. So we're going to do a lot of these electron configurations. They represent how many electrons are in each energy level. 2 in this one, 2 and 6 on this energy level, 2, 6, and 10 on the third energy level. So we're representing where all of these electrons are. There are some shortcuts. You can kind of figure out where you're going to end based off of how off about where you are with the element. So like a second ago I said sulfur, and sulfur was right here on the periodic table, and so I knew that all of the 3 P's are there together, and then iron was right here, and so I knew that the 3 D's are right there, and then zirconium is right here. And so this is actually off Bose order hidden right on the periodic table. So look at off Bose order, look at this periodic table at the same time. See 1s2, next slide, 2s2, next slide, 2p6, next 3s2, next slide, 3p6, 4s2, 3d10, 4p6, 5s2, 4d, and this is the same order that you see on off Bose order right there on the periodic table. And it's just a nice little kind of shortcut. So we also talk about how electrons move, how they spin. Electrons occupy those orbitals, and they're moving through those orbitals in a direction, and we call that direction their spin. One thing that has to happen, electrons have to have opposite spin to be in the same orbital. And we represent their spin with these arrows. You see how these arrows are pointed in an opposite direction? It means one electron is spinning one direction around the orbital, and the other one is spinning the other direction around the orbital. These are actually just factors inside that math problem we tried not to look at a couple minutes ago. These 2 electrons, these 2 arrows, are spinning the same direction. That cannot happen. That is not possible. If they're spinning the same direction inside the orbital, they push each other away, and one of them has to leave. Also, an electron is stuck in its spin direction. You can't really flip an electron easily. They can involve something weird, but so the first kind of rule or principle we're going to learn is called the Pauli exclusion principle. The focus on the word exclusion here, it excludes same spin. So 2 electrons must have opposite spin. It excludes this situation, it excludes that situation. They must be opposites to be in the same orbital. And if this is a 1s orbital with 2 electrons, we're talking about a helium atom. So helium atoms have 2 electrons moving around their sphere close to the nucleus. They have to have opposite spins. Hund's rule down here. Hund's rule is about, let's kind of focus on a couple words. All the orbitals must have 1 electron before they can have 2. So let's say that we were doing something that was, oh, that already says 3p4 right there, doesn't it? So we're doing a 3p4. These p orbitals, one's on the x, the y, and the z axis, have to have electrons in them. So I have 1 electron, and we're doing p4. 2 electrons. Oh wait, 3p4. Which element is this? Let me see this element ago. Yeah, sulfur. 1s2, 2s2, 2p6, 3s2, 3p4. So what are those 4 electrons doing? Let's spread this out. Remember, there's spaces, and those electrons are going to spread out in those spaces. But drawing these pictures is impossible by hand. So instead we use these amazing looking little lines or boxes. So we're saying the 3p has 3 orbitals, and there's electrons in them. And oh, there we go. There's the 4 electrons. They have to be 1, 2, 3. Put 1 electron in any orbital before you can have 2. Oh, there's the 4th one. And then these 2 orbitals are both half filled. And that half filled gives sulfur some of its fancy properties we're going to use later in the year. So the way this works is real simple. You draw arrows starting with the lowest energy level and you fill it all the way up to the top. I can't really draw these arrows on my laptop here, but start to fill in the arrows. If there's 2 electrons in a space, make sure they're in the opposite direction. If there's here with this 3d4, you'd have to go 1, 2, 3. I can type. You can do 1 here, 2 here, the 3rd one here, the 4th one there. If there were more, you'd go 5, and then you would come back and put the 6th electron, and you would put the 7th electron, the 8th electron, the 9th electron, and then the 10th electron would go here. But when you put those into here, they would have to have opposite spin. Alright, so as they go back into the orbital that's already got 1 in it, the second one has to be moving in the opposite direction. They have to have opposite spin. Alright, so take a couple minutes and fill out the sulfur and the bromine energy diagrams in your notes. So as you probably noticed with bromine was really long. I mean, it just kept going and going, and you had so many electrons you had to fill in. It's 35 electrons. It really gets to be a pain after a while filling it all in. I'm not gonna lie. I mean, it takes a long time to do some of these. And I think with bromine, you end all the way up here in the 4 P's, and you should have 1, 2, 3, 4, 5 electrons at the very last level that's in this energy diagram for bromine. But thankfully there is a shorthand. The shorthand is reliant upon you knowing which elements are the noble gases. So let's go back to a periodic table and make sure we all know where the noble gases are. The noble gases are the last column on the periodic table. They are right here. And these noble gases are all spectacularly awesome because they are what we call full energy levels at the last space. They're all, that font couldn't be smaller, could it? Let's adjust that so people in the back can see it too, not just people with telescopes. Alright, so every element that's over here, let's see, neon is 2p6, argon is 3p6. What's below argon, people? Krypton. Why did I put my periodic table so far away from me? Krypton is 4p6, xenon is 5p6, and then radon. Everyone likes radon. No, that's a lie because it's dangerous. Radon is 6p6. All of these elements are 6p6 or 4p6 or 3p6, and that p6 configuration is special mathematically. They are non-reactive elements. So we use the noble gas as a basis for our shorthand. So instead of writing potassium's full configuration, here it is right here, and it's in your notes also. Instead of writing, no, it's not in your notes. I'm looking at your notes now. Instead of writing out the full configuration, we can just do a shorthand. So let's compare these two. Argon goes from 1s2 to 2p6 to 3p6. Potassium, same thing, but since potassium has 1 more electron, we gotta go down 1 more energy level, and so the difference is just a smidge difference. And using the shorthand, we could say potassium looks like argon plus that extra space. So I've tried to color code it here in the notes on the screen. The blue is a match and the red is the extra. So argon matches potassium, except it's got this little extra. So that's what we would write. We'd say potassium looks just like argon plus the extra piece. And you have to figure out what the extra pieces would be, which is where kind of knowing that here is argon right here. It's 1, 2, 3 levels down, and it's a P6. That's really going to help you out because it's a nice shorthand. So I think this is where we're going to stop for today. We're going to stop on the noble gas configurations because the bell is literally going to ring in a second. Your homework is, of course, to practice doing these, and you'll see worksheet 1 has lots of this stuff, and study for your quiz, that polyatomic ion quiz. All right, good luck, ladies and gentlemen, and make flashcards for that polyatomic ion quiz. See you soon.